Unlock the potential of artificial intelligence. Welcome to Deep Learning and Generative AI.
This is Week 11, Part 4. Our core mission is the transition from messy, experimental AI ideation into reliable, governed enterprise software. This diagram illustrates how we refine that tangled web of raw experiments into a straight, production-ready pipeline. Look at this mock interface detailing the Chevy chatbot blender. This occurred when a raw large language model was deployed without proper guardrails. The customer-facing bot was easily tricked into doing algebra homework and agreeing to sell a car for $1. The underlying cause of failures like this is stochastic generation. Generative systems are non-deterministic. The exact same prompts can yield wildly different results every time. There are two other technical hurdles here. First is extreme prompt sensitivity, where a tiny text change breaks your entire data schema. Second are system-level safety risks, like adversarial prompt injections that trick the application into leaking sensitive information. This chart compares legacy machine learning operations to modern LLMOps. Notice the top row on scale. We are managing a 1,500 times increase in model size, moving from 200 million parameter models to orchestrating 175 billion parameter generative engines. Pushing a raw generative model into unpredictable user environments leads to catastrophic business failures, unless we implement an entirely new operational framework to contain it. This diagram illustrates the reality of production deployment. We must manage a multi-component composite AI system surrounding a foundational core. We cage the model safely using specialized modules. On the right, context modules feed the model specific facts using RAG. RAG, or Retrieval Augmented Generation, is a pipeline pulling external data into the prompt before the model answers. On the bottom, control modules apply strict safety guardrails to filter the text. Variable text outputs make traditional exact match unit testing obsolete. As shown here, engineering teams transition to evaluation-driven development. This relies on golden sets, carefully curated, high-value test cases that grade the model on semantic rubrics rather than expecting a single, rigid string of text. Looking at this interface, we see how variables are controlled at the input stage. Prompts function as executable specifications that must be locked into immutable versions using prompt registries. This allows developers to track changes and roll back to stable production aliases anytime. To control an inherently unpredictable text generator, every surrounding layer, from prompt inputs to final evaluation criteria, must be locked down into rigid, immutable infrastructure. This chart shows a common observability problem. A request can succeed technically while failing semantically by returning toxic or incorrect content. To solve this, we use OpenTelemetry span tracing. OpenTelemetry is an open-source standard that tracks the exact timing and path a request takes through an application, giving us granular visibility into every step. Monitoring RAG pipelines require evaluation metrics that correlate with actual application performance. For example, BLUE, an old metric that measures exact word overlap between machine translation and human reference, is useless for evaluating open-ended generative AI. This diagram maps out the three specialized signals required to prevent hallucinations. First, we check retrieval relevance to ensure the right documents were found. Second, we verify context packing, making sure the prompt includes the best evidence. Finally, we measure groundedness, confirming the final model output actually relied on that retrieved evidence. This continuous integration and deployment loop, or CI/CD, ties these engineering concepts together. CI/CD is an automated process for frequently building, testing, and deploying code. As you follow the center column, you can trace the automated flow from strict offline evaluation suites in Step 3 down to live online A/B testing in Step 6. True LLM observability requires semantic verification at every single microstep of a prompt's journey, long before it ever reaches a user's screen. We must translate these code pipelines into actual enterprise value. This panel outlines the 4 foundational goals of LLMOps: reliability, scalability, robustness, and security. This table shows how those engineering goals are anchored to business reality. Internal Service Level Objectives, or SLOs, which has specific targets for system performance, map directly to measurable external KPIs, such as customer satisfaction scores. Who actually built this? This timeline maps out the modern AI team structure. Data engineers design the massive pipelines on the left, while AI engineers and ML scientists build the initial proofs of concept during the ideation and experimentation phases. The ultimate project owner for production is the LLMOps engineer. Looking at the day-to-day timeline on the right, this hybrid role requires upskilling existing talent to manage infrastructure as code, orchestrate vector databases, and troubleshoot end-to-end latency traces. An AI pipeline is only as reliable as the team running it. Without translating technical traces into business metrics and staffing specialized operations talent, generative AI remains an expensive academic experiment. This maturity model assesses organizational readiness. At the bottom, Level 0 operates in experimental silos without formal risk assessment, exposing companies to early chatbot failures. Organizations must ascend to Level 2, full LLMOps, where deployments are optimized for scale and real-time monitoring. This graphic summarizes the definitive playbook required to reach that top level. It demands a transition to evaluation-driven development, establishing strict offline gates for deployment and upskilling teams to handle dynamic scaling. Reliable generative AI deployment requires a rigorous operational discipline that moves beyond the experimental sandbox into reproducible, monitorable, and governable infrastructure.